In the previous videos, we've had a hidden assumption that the working substance in our thermodynamic cycles is an ideal gas. But most of the thermodynamic cycles that are used in industry for productive reasons are not done with ideal gases. Think of the first heat engine that existed. It was a steam engine. What does a steam engine do? It boils water. The pressure of the steam moves the piston. You have water in a liquid form turning into gas to expand, and then condensing back into water at a later point in the cycle. So that's definitely not ideal gas behavior. We have a phase change in the middle of our thermodynamic cycle. And to handle that, we won't be able to use ideal gas equations that include the ideal gas constant R or the degrees of freedom F. We'll have to use tabulated values for the specific fluid that we're using. But there are a couple of general properties of all cycles with phase transitions that we can discuss first. The first thing that we must understand is what a phase transition looks like on the PV diagram. Let's consider a basic gas mixture to liquid phase transition, like we might have covered in the calorimetry section of the course. If we keep our system at a constant pressure, for example, and start at a very high volume, in order to have a constant pressure and a high volume, the substance is going to be in a gas phase. If we compress the substance down to a very small volume while maintaining that temperature, that forces us implicitly to remove heat from the system, whether it's a gas, liquid, or otherwise. So when we find ourselves in the low volume region of the PV diagram, we are at a liquid phase. So if we stay along an isobar of constant pressure, beginning with a high volume and slowly compressing or removing heat, we're eventually going to reach a point where a bit of liquid begins to appear. So we have a segment of volumes here in the middle where we have a mixture between gas and liquid in the same space. Eventually, we get to a small enough volume and a cold enough temperature where 100% of the mass is now in the liquid phase, and as we continue to cool or decrease volume, it will stay all liquid from then on. So that's what the PV diagram looks like for a gas to liquid phase transition at a specific pressure. If we consider a different pressure, let's say one that's a bit higher, we get a similar type of diagram, except for the fact that the mixture does not exist for as wide of a range of volumes. Why does this happen? We're at a higher pressure, so the gas can remain as a gas for longer before it reaches that conversion point. As we go to lower pressures, the transition point from gas to some liquid occurs at even higher volume. This family of segments here forms an envelope. That looks something like this. We'll discuss the top point in a later lecture, but this is called the critical point. It's a special temperature, volume, and pressure at which the distinction between liquid and gas vanishes. This envelope divides the PV diagram into four regions: pure liquid, pure gas, liquid-gas mixture, and what's called supercritical fluids up here. We're not going to deal with any cycles that use supercritical fluids, though we will investigate them more when we talk about phase transitions in general. The second important property of phase transitions on the PV diagram is about the mixture area. If you recall when we discussed calorimetry and phase transitions, In the mixture, the temperature remains constant. The pressure remains constant. The only thing that changes is the fraction of mass in one phase and the fraction of mass in the other phase. This means that when we're in the mixture region, all of our thermodynamic properties are a weighted average between the properties of the liquid at this edge, which I'll call L, and the properties of the gas at this edge, which I'll call G. Imagine that we graphed something like the density of the system between the point L and the point G. At the point L, the system is purely liquid, so it has some density equal to the density of the liquid. At the location G, we have a specific temperature and pressure, so the gas has a specific density. Between L and G, we're forming a mixture between some matter in this phase at L and some matter at this phase in G. There isn't really a distinct phase of matter in between here, we're just forming a mixture. So a property such as density varies exactly as a line between the point L and the point G. This is called a linear interpolation, or it's also called the lever rule. Any other properties such as molar volume, internal energy density, entropy per mole would vary in exactly the same linear way throughout the mixture region. The way we can apply the lever rule quantitatively is by defining a quantity called the quality of the mixture. The symbol for quality is a lowercase x, and it ranges from a value of 0 when the mixture is 100% liquid to a value of 1 when the mixture is all gas. So our graph down here could be interpreted as a graph between x equals 0 and x equals 1. For a quantity such as density, then we can write down the exact linear interpolation formula. The density at a specific quality level would be equal to the density of the liquid plus the density of the gas minus the density of the liquid times the quality factor. We can see how if x was 0, the density would be equal to rho sub L, and if the quality was 1, the rho sub L's would cancel, and we would get the density of the gas. Any other quantities, such as the entropy, or the volume, has the exact same form of its relationship to the quality factor x. This means that if we define the point in the mixture by its volume, we can solve, say, for the quality value of a specific volume, knowing the volume of the gas and liquid at that pressure line, and then use that quality value to predict the amount of entropy per mole or the density or any other quantity along this mixture line. When we deal with a substance that undergoes a phase transition on the PV diagram, we can't use the ideal gas laws or anything like that. If a formula has the ideal gas constant or the degrees of freedom, it probably can't be used. So what do we do instead? Well, unfortunately, we just have to look up tables. Liquids are complicated, and there's not good formulas that just give us an easy prediction. I've uploaded a set of what are called steam tables to Sakai. I encourage you to download those and open them up on your computer before continuing with the rest of this video. Let's use table A5 to try to draw a somewhat accurate representation for this phase transition envelope for water. The first point I'm going to draw on here is way at the end of table A5. There's a final row that doesn't quite match the pattern of the rest. Its pressure is 22.064 megapascals. The reason this row is special is it represents the critical point of the water-gas phase transition. If you check the columns for saturated liquid and saturated vapor volume, you'll see that they are the same. This means that the phase transition disappears. Let's mark this point at 22 megapascals and 3.1 liters. That's the critical point. Now let's get our bearings with this table some more by going back to the first page and searching for the row that is labeled 101.325 kilopascals. This is atmospheric pressure. We can see that the phase transition temperature, 99.97 degrees Celsius, is the phase transition temperature for the boiling of water. If we check the volume of the fluid, it is 1.043 liters. Water has 1 liter per kilogram. If we check the volume of the gas, 1.6734 meters cubed, we get the volume that would be present for water vapor at the boiling point for 1 kilogram. The other value we can look on for here that we might recognize is the column for the enthalpy of evaporation, H sub Fg. If you go to that column in the row for 101.325 pressure, you see that it's 2,256.5 kilojoules per kilogram. This is actually the latent heat of vaporization for water. It's the difference in enthalpy at constant pressure. If we try to draw this row on our graph, it would be way too low in pressure and way too large in volume to fit. So to fill out our graph, let's look at some of the other pressures that are a bit higher. First, I'll go to 5,000 kilopascals or 5 megapascals. At this pressure, the volume of the liquid is 1.286 liters. And the volume of the gas is 39.4 liters. Let's move up to 10,000 kilopascals or 10 megapascals. At this pressure, the volume of the liquid is 1.45. And the volume of the gas is 18 liters. The next row we will plot is 15 megapascals. The volume of the liquid is 1.6 again. And the volume of the gas is now 10.3 liters. We can connect these dots to draw the envelope for water. Now let's practice using this steam table to answer some questions about the values of various quantities at various volumes. Tables A4 and A5 can be used to get any of the quantities, volume, energy, enthalpy, entropy, pressure, or temperature, at any point along the envelope or within the mixture region. Let's ask a question. If we set up a sample of water with a pressure of 10 megapascals and a volume of 10 liters, what percentage will be water and what percentage will be steam? In other words, let's solve for the quality. To do this, we first need to look up the volume at that pressure for the pure liquid and for the pure gas. Using the table, we see that at 10,000 kilopascals, the volume of the liquid is 1.452. And the volume of the gas is 18.028 liters. We can now use the lever rule to solve for the quality X. The actual volume on the left is equal to the volume on one side plus the difference between volumes times the quality factor. This gives us a quality of 0.5156. We should always expect the quality value to be between 0 and 1. With the quality value known, we can now answer a host of other questions about this system at this specific pressure and volume. For example, what is the entropy per kilogram? To solve for this, we will now use the lever rule, but in the opposite direction. We again need to look up the entropy in the pure liquid and the entropy in the pure gas phase. The entropy of the saturated fluid is 3.36 kilojoules per kilogram per Kelvin. The entropy of the saturated vapor is 5.6159. Kilojoules per kilogram per Kelvin. The entropy of our exact sample at 10 megapascals and 10 liters will be equal to the entropy of the liquid plus the difference in entropy times the quality factor. This comes out to 4.523 kilojoules per kilogram per Kelvin. So the entropy of a sample of water held at a pressure of 10 megapascals and a fixed volume of 10 liters has an entropy of exactly 4.523 joules per gram per Kelvin. The similar procedure can be used for any of the other quantities we might want to know, such as internal energy or enthalpy. Tables A4 and A5, in addition to the lever rule, provide us with the values of any quantity we might need anywhere on the envelope or in the mixture region. If we want to know about the properties of the system when it is in the gas phase, we need to specify two values, the temperature and the pressure, or the temperature and the volume, or the pressure and the volume. This is why table A6 is divided into grids. Each grid square covers a different pressure, and the rows cover different temperatures and volumes. Let's look for a specific location on our graph. Let's say we're interested in the properties of water steam at 15 megapascals of pressure and 25 liters of volume. That's 25 liters per kilogram. So let's flip through table A6 until we find a pressure that's labeled as 15 megapascals. I don't find this one until the top left square of page 921. If we now go down the volume rows, we are looking for a volume of 25 liters. We don't get this row exactly, but we do have rows for 24.9, 26.8. The row for 24.9 is fairly close, so let's use those values for now. The internal energy would be 3209 kilojoules per kilogram. The enthalpy per unit mass would be 3583 kilojoules per kilogram. And the entropy per unit mass would be 6.679 kilojoules per kilogram per Kelvin. This is how we determine the properties of a purely steam system over to the right side of the envelope. The last table for water is labeled compressed liquid water, table A7. This table lists the properties of water to the right of the envelope. This is how we find the properties of a steam system when it is purely gas to the right side of the envelope. The final table for water is table A7. This is titled compressed liquid water, and it gives the properties of water to the left side of the phase transition envelope. There aren't as many entries here for pressure and temperature because we don't usually compress water very greatly.